All right, welcome to Friday. Go ahead and get out your homework. So 1 through 10, all. It was basically calculating slope. All right, let's see. Number one had an A, B, and a C. So 1A is 2/3, B is 2/3, and C is -3/2. Remember, perpendicular lines are opposite reciprocals. Number two, A is -2/5, B is -2/5, and C, the opposite reciprocal, will be 5/2. Number three, so you have four segments and it's asking you the slope of each one. Well, it's a parallelogram, so if you do the left side, the right side is the same. If you do the top, the same as the bottom. Well, the top and the bottom are both horizontal lines. How do you know that? Because OG, the bottom line there, is the x-axis, so therefore it has a slope of 0. So the opposite side, which is EF, also has a slope of 0. And then the two other sides, when you do the calculations for the slope, you get 7/2. Okay. Okay. That was number three. Number four, it's that other diagram there. This was a little bit more challenging, but it does say, once again, it says it's a rectangle. Rectangle is a parallelogram, so opposite sides would have the same slope. Now, the issue with this one is that they only give you 2 points. So here's the basic idea. So you can calculate the slope of two of the sides easy because you have 2 of the points. The third and the fourth side, remember, since it's a rectangle, you know that you have right angles, so therefore they are perpendicular, so you would get opposite reciprocals. So that's how that's done. So basically the slopes are 1 and -1. And there should be 4 answers there because you have 4 sides. So 1, 1, -1, -1. All right, 5. Well, apparently this was the lesson of they wanted to use a whole bunch of letters here. So 5 has an A through an E. All right, so A is -3, -3. B is, well, they're parallel, so obviously their slopes have to be equal. C, their slopes are 1/3 and -1/7. And D is, well, their slopes are not equal. Those would be the two sides this was a trapezoid of some sort. So these are the two sides the two legs of the trapezoid. So their slopes are not equal. There would be no trapezoid. I'm thinking through my head. Yeah, no trapezoids where their slopes would be equal. Their distances could be equal if it was isosceles. Uh, that was C and D, and then last one E. It's trapezoid, as I just said. All right, 6 also has an A through D. A is -1 and 1. It's a rectangle slash. No, it's parallelogram. Oh, I get it. So they don't tell you it's a rectangle at the start. They just say it's a parallelogram. They give you enough points to calculate. Okay, A is -1 and 1. B is well, remember, they have to be perpendicular because the products of the slopes would equal -1. And since the slope was 1 and -1, 1 times -1 is -1. Uh, okay. Well, it's a rectangle because one of the angles, we just proved in the previous one that their slopes are opposite reciprocals. That means they're perpendicular. So that means you have a right angle. Quadrilateral with one right angle. We've seen this before. We use the product that interior angles add up to 180, or you can say opposite sides or opposite angles of a parallelogram are supplementary. Any of those work as well too. And then lastly, D, 3, -1. 3, -. So how did you get D? Well, you have to get a certain value for either the slope or the same side slope, or the side. If you use the side that was perpendicular, you'd have to get to an opposite reciprocal. Any one of those, I'm not sure how you guys solve that. I probably would have done the easy way, and just once I calculated the one slope, I would just figure out what, because you have one of the points, you just don't have the second point, so you just use whatever numbers get you to the same slope, and that would be 3, -1, xy. All right. Number, let's see, 7. Find the slope of each side, and it's a triangle. So there's going to be 3 answers here. All right, so AB is 3/7. Let's see, AC is -5/2, and BC is 8/5. Now the altitudes, remember, that would be perpendicular to one of the sides. So the altitude to AB, right, would be, well, the opposite reciprocal of 3/7 would be -7/3. See how that's done? The altitude to AC would be 2/5, and the altitude to BC would be -5/8. All right. Number 8's done the same way. AB is 7/2, AC is -3, and BC is -2/5. Those are the slopes. And the altitude to those sides would be the opposite reciprocal, 90 degrees. So the altitude to AB would be -2/7, the altitude to AC would be 1/3, and the altitude to BC would be 5/2. All right. So 9 and 10, the last two, use slopes to show that it's a right triangle. Well, you got three sides. As long as two of those sides are opposite reciprocals of each other, then you know you have a right triangle. So for 9 and 10, unfortunately, if you choose poorly, you may have to do the calculation 3 times to figure out if, in fact, you do have opposite reciprocals for any of the slopes. So let's see. On number 9, the answer is yes, it is an opposite reciprocal. For two of the slopes, one of the slopes you get 6/5, and the other one you get -5/6. So that would be RS and ST. RS is 6/5 and ST is -5/6. Opposite reciprocals. So right triangle. B, it turns out that RS and ST are your right, the sides that form the right angle. RS, the slope is 1, and ST, the slope is -1. That was a lot of work for one homework assignment. Okay. Well, the standard answer question 1 of the Google Forms. Well, ladies and gentlemen, we have reached the last day of new material. So once again, we're not going to finish 13. We're not going to get to chapter 14. So you are missing something. We'll be okay with what you're missing. If you are truly curious and you're, hey, I really want to finish the book or whatever, we can do this over the summer. Email me if you want to truly finish the book. I can give you the lesson plans for all the material if you're interested in that. If you're not, then you have to take my word, but we'll be good to go moving forward. For most part, for PSAT, SAT, ACT, the stuff that we have covered so far will do you just fine for doing well on those tests. There is there's a lot of emphasis is put on geometry in all of those tests. However, most of it is all the previous stuff that we've done. The basic logic of geometry, remembering, all the stuff we have for right triangle. There's other things that we've done in geometry that we will see again next year in Algebra 2, pre-calc, calculus, that gets reinforced. But the logic part of geometry, trust me when I say we've done a really good job of that, and you're well prepared to do well in the future. Not to say that you shouldn't get a good study guide for PSAT and SAT, ACT, but the geometry piece is not something you're going to encounter and say, I never learned this type thing. You're going to say, oh, I remember learning it. You might have to brush up on it, that sort of thing. Wow, that was a long speech for such a little thing. All right, here's your homework, 1 through 26 all. We're about to do something that's ridiculously easy and looks ridiculously complicated. And if I were to say, do this all by yourself, you'd probably be lost. But trust me when I say it is easy, and I'll guide you through it. All right, last class. Okay, vectors. For those of you that were around, you saw a little bit of this in 8th grade. You will see a lot of this when you take physics, which I believe is junior year high school at our school. Yeah, that's right, junior year. And we're going to see it today as well, too. For vectors, occasionally we talk about vectors in pre-calculus a little bit, calculus a tiny bit as well too, but for the most part, the next time that you see vectors is going to be your physics class, and boy, you're going to do a lot with vectors. Okay, so that's kind of the introduction. So depending upon, for those new kids, you may or may not have even heard of this thing called vectors before, depending upon who your science teacher was in previous years. Vectors are not necessarily a 7th or 8th grade standard. I know Mr. Surratt introduces students, and I also I don't know the detail that he's introduced or the level that he's introduced you to. All right, so these are four basic statements about vectors. It's a really, really easy concept to understand, and the math behind it is really easy to do, and it's going to be very useful in physics. But there's a lot of new vocab and definitely new techniques that I'm going to show you today. So this might be one of the ones where you have to, I don't know, listen to the class twice. I pretty much follow what's in the book. The book does a pretty good job, a little bit more shorter or succinctly than how I describe it, but it matches what I teach as well too. But there's going to be lots of new vocab. There's also symbology that's new as well too. This comes out of left field, and it's in this chapter specifically because it deals with things on a Cartesian coordinate plane. All right, so let's go. Generally, when we talk about motion, I mean anything in motion. I mean we're all in motion. We're on a object in space that is moving. The Earth, our solar system is moving. Our galaxy is moving. Even as you are sleeping, you are moving, and I don't mean that you turn to the side. I mean you are physically moving. You just relative to the room that you're in, it doesn't feel like you're moving. But when we talk about motion, we talk about basically a couple different things. Well, the first is the force. You know, how much force is used to actually impart motion upon an object. Once an object is in motion, it has a velocity, and that's a comparison of how far it moves to time. That's what velocity is, distance divided by time, miles per hour is an example of velocity. We also have this concept of acceleration. Acceleration is how does velocity change as compared to time. So when you talk about acceleration, that might be feet per second, and that's your velocity changing for time. Those three ideas right there, force, velocity, and acceleration, all deal with motion. And if you've had a great science teacher, you're all familiar with the formula force equals mass times acceleration. Okay, that's a basic form that describes motion. For our purposes, we're gonna really focus in on two things. Motion has two parts to it that we will look at today. One, it has a direction, right? When you are moving in a direction, and there's also in terms of acceleration and mass, there's something called the intensity. Are you moving fast or are you moving slow? In math terms, we call that the magnitude. That's also the same term in physics. Now, we are going to introduce you to this concept, if you haven't already been introduced to it, of called a vector. And a vector is a mathematical term that expresses two things. It expresses for an object, right, its magnitude, how much force there's involved, and also what is the direction of that force. So we're going to call this thing a vector, and a vector expresses that. So it's any quantity that has both a magnitude, hey, how fast or how much force is being applied to something, and what is the direction of it. We call that a vector. Specifically in geometry, we are going to draw vectors on a coordinate plane. It's going to look like a ray. So on the coordinate plane, when we draw these things, it's going to look like a ray. However, its symbology, I mean, how we name it on a piece of paper, will kind of look like a ray, but it actually is the vector symbol. So this is the vector symbol, and you can see it sort of looks like a ray. It's an arrow with a little piece of it missing. Whenever you see this, we're talking about vector AB, and that's how it's read, vector AB. And remember, it describes two things. It describes what's the magnitude of the force, right? How much force is being applied to something, and what direction. So when we draw this vector on the coordinate plane, how long, and now I said ray question mark, we're going to draw it as a ray. When we draw it on the coordinate plane, right, the XY axis, we're going to draw a ray, and the length of that ray tells you its magnitude, right? Little error, a little magnitude. Long arrow, a large magnitude, right? So the length of the ray describes the size, intensity, or strength. Any one of those words would be okay. In general, we say what's its magnitude. So a long ray, big magnitude. Short ray, small magnitude. we are going to describe this in terms of an absolute value. And if we calculate the absolute value of the distance of the ray, right, we can't get a negative value. So we're going to actually use the distance formula. That's how we're going to figure out how, what's the size, intensity, or strength, the magnitude of that ray, right? And that's half of what a vector shows us. Well, the other half is what's the direction, and believe it or not, it's where the ray is pointed. Right? If the ray is pointed up to the left or down to the right or straight across to the right, the direction where the ray is pointed is the direction of the vector or the force. So big picture. Oh, one last thing. So here's the symbology for the direction. And now this is when you're first, you got to pay attention. If you're just kind of lightly listening, you're not going to get this. The direction of the ray is equal to the change in x, comma, change in y inside parentheses. So check that out. AB, vector AB, where is it pointed? You put an equal sign, you put an open parentheses, you put the change in x, comma, change in y. That certainly sounds like really complicated, or it sounds like it, but it's actually easy. It's easy. Keeping it straight in your mind, that's the harder thing to do. The easiest thing to do now is just do some examples. So on the examples, right, we're going to be answering 3 questions. 3 questions are this. They're going to ask you to sketch the vector. We're just going to draw a ray on a coordinate plane. They're going to give you 2 points. It's going to be simple, trust me. The second thing is, it's called find the vector. So find the vector is where you're going to be calculating the direction of the vector, also an easy thing. And then lastly, you're going to be calculating the magnitude. You're going to be using the distance formula. So first one easy, the last one also easy. It's going to be easier if you do them in this order. Sketch the vector, find the vector, and then calculate the magnitude. And you'll see why I say to do them in this order. So how about we just do one? You do need graph paper to do these. It's very helpful. Okay, so here's how the setup. So they're going to give you 2 points. The difference, remember, between a ray and a vector, right? A vector, the ray actually comes to an end at some point, right? I mean, not physically in the sense of the force goes away, but visually it stops. Just remember, for geometry, a ray goes on forever. But the difference between a ray and a vector visually will have no difference on the coordinate plane. In fact, you're going to have to be told that it's a vector because otherwise it looks like a ray. So notice I have 2 points there. I've got point P, I have point Q, and it says it represents vector PQ. Notice the vector symbol there. It's kind of like it's missing a little part of the ray there. Okay, so remember 3 things. Draw, calculate its direction, and state what it equals, and then do the magnitude. All right, so sketch the vector, that's the easy one. You got P and Q. You just put a dot on P, put a dot on Q. Remember, it goes in the direction of from P to Q. Yes, I realize my point P is slightly off there, but you get the basic idea there. That's called sketching the vector. When you take this in physics, in 2 years from now, 2 years from now, you're juniors. When you sketch this vector, it's going to have a bit more complexity to it, but you'll remember it from this class. Okay. So we got PQ there. Step 1 is done. We've sketched the vector. Step number 2, it's called find the vector. Find the vector. Find the vector just means what direction is it going? And there's going to be a formula for this. Remember the formula for what the vector is equal to. In other words, the direction of it it's 2 parentheses, a comma in between. It looks like a point, but it's going to be the change in x, comma, change in y. And literally all it means is, it's kind of slope in reverse, except it's not a fraction either. And you have to do the x first, and then you have to do the y. So the change in x. To go from P to Q, how many squares, how many tick marks, right? Or use the change in x values to do this. I'm going to use the change in x values. So let's see. X in Q is, what, 1? And the x in P is -5. So this would be 1 minus -5. Remember, we subtract the difference between the largest x value and the smallest x value. You could also put this in absolute value as well, too. Comma, the change in the y values. Change in y values, let's see. That would be 2 minus 4. Do you see where I'm getting those numbers from? And it feels like we're doing slope here. We're just kind of doing the opposite of slope. That's imprecise terminology. We're not doing the opposite of slope, but there's a slope feel to this. So let's see, 1 minus minus 5 would be 6, 2 minus 4 would be negative 2. So long story short, what does vector PQ equal to? It equals to 6 comma negative 2. So what does this equal mean? This is telling us the direction. The direction of this vector. Where is the force going? It's going in the direction of 6, negative 2, not the point 6, negative 2. It's not going to the point 6, negative 2. It's going in the direction of change in x's is 6 and the change in y is 2. Or another way of thinking this, it's going to the right 6 down 2. I think that's a better way of describing this. As soon as we say that, it sort of sounds like slope, okay? But it's a vector, not slope. Okay, so we've done two of the things. The last thing is we got to find the magnitude. Now that's in absolute value because remember, the magnitude or how much of something can't be negative. It's going to be a positive value. And remember the distance value, distance formula, since we take the square of something, we don't have to worry about it being a negative value because we're taking the square of something. Any negative number squared is positive, okay, in parentheses. Okay, so I'm going to really mess with you, and I'm going to do this in a little slightly different order, all right? And let's see, the distance formula is the square root of the change in y value squared plus the change in x value squared. I'm just going to do this in a slightly different order. You'll see why in a second. I'm going to say it's the square of the change in x values plus the square of the change in y values. Why did I do it that way? Look above. Look at what's in yellow there. 6 comma negative 2, that's what you have to actually square. We've already done that calculation, notice. So the distance formula isn't hidden inside the previous one, finding the vector, but it's the same values that we're going to use. So if you find the vector first, then to find its magnitude, you just take the two values, square them, add, take the square root. Take a look at those numbers, 6, negative 2. See what I just did there, right? PQ, what's the magnitude of vector PQ? It's the square root of 6 squared plus the negative 2 squared. Where did I get the 6 negative 2? Well, it comes from the vector itself, 6 negative 2. That's the direction of it. Hey, that makes our life a whole lot easier. Okay, 6 squared is 36, negative 2 squared is 4, 36 and 4 is 40. Let's see, that would be 4 times 10, so 2 root 10. So the magnitude of vector PQ is 2 root 10, and the vector PQ is 6 comma negative 2. Those are the three things that we have to do for, I don't have my book, oh yeah I do, right here. Let me pause for a second. Yeah, that's the first half of the homework right there. Those three things right there. You want to do another one? Yeah, let's do another one. Okay, so same drill here. We're given a vector PQ. I'm lazy, I didn't change the letters there. And we're told P is at 2, 2, and Q is at 6, 5. So remember the three things. Sketch, easy. 2, 2, 6, 5. And then label. So that one ray right there, it's not a ray, it's a vector, shows us both the magnitude. Remember, long arrow, long magnitude, short arrow, smaller magnitude. Then it shows us the direction. So we're asked to find the vector. What we're doing is we're finding the direction the vector goes. So how do you do that? It's the change in x, comma, change in y. Change in x, comma, change in y. It looks like an ordered pair. It's not. So let's see. The x values, that would be 6 minus 2, and the y values would be 5 minus 2. Okay? And you're like, well, can I do them in another order? Well, no. Remember, it's p to q, not q to p. Okay? All right. Okay. 6 minus 2 is 4. 5 minus 2 is 3. So we get 4 comma 3. That was pretty easy. Pretty easy. Now, if it was, all right, let's reverse the order there, Q to P, right, then you would get some negative values there instead, okay? Magnitude. So let's find the magnitude of PQ. Oh, by the way, let me back up one step. So what does 4, 3 means? It means the vector is going to the right 4 and up 3. And look at the picture. That's exactly what's going on there. Right? If we had gone from Q to P, then it would be left 4, down 3. Okay? All right. Okay, magnitude is just the distance formula. I'm going to use the shortcut here since I already found the vector 4, comma 3. Then all I can do is take the square of both, the sum of the squares of both of those, take the square root. Okay? Or the square root of the squares of the square root of the sum of the squares. How about that? Finally got it right there. All right, 4 squared is 16, 3. Where did I get the 4 and the 3? Look above in yellow. That's where the 4 and the 3 came from, right? Remember, change in x values, change in y values. That's what the distance formula does, right? It says, what is the difference of the x values squared plus the difference of the y values squared, and then take the square root. Well, since we already did, I don't know if you want to call it half, right? It was certainly a third. If we did a third of that already in the first step, or middle step there, find the vector, why don't we use that information to calculate the distance? And we did. So 16 plus 9 is 25. That's 5. Therefore, the magnitude is 5. Okay. Notice since it's an absolute value, you can never get a negative magnitude, right? So the magnitude might have a direction. So think about it this way, going forwards and backwards. A car that's in forward and backwards. So magnitude would equate something to the force of what it takes to get that car moving, right? Well, if you apply that magnitude in an opposite direction, right, the direction can be negative, right? But the force would still be the same. In other words, if you go forwards 5 miles an hour versus going reverse 5 miles an hour, you're talking about the same amount of force, but in opposite directions. So directions can be negative, but magnitude will always be positive. Okay, I have this one here to do by yourself. Go ahead and try those 3 things all by yourself. And then, well, you can't put a graph in Google Forms. So we're going to skip that part. But yeah, please pause this, try to get to the answer yourself, and then play the video and confirm that you're getting the right answer. How'd you do? All right, so the sketch, that was pretty basic. So -2, 4 to 3, 2. Okay, so find the vector. In other words, the direction of the vector. So remember, that's the change in x, comma, change in y. So the change in x would go 2 minus -2, and then, I'm sorry, 3 minus -2, comma, change in y, 2 minus 4. Okay, so 3 minus -2 would be 5, 3 plus 2, and 2 minus 4 is -2. So we get 5, -2. And notice, look at the ray there, that's the vector. Look at the ray that we drew there, and it's clearly going right 5, down 2, right 5, down 2. All right, that's pretty easy. To find the magnitude, we just take the sum of the squares and then take the square root. So that's what, 25 plus 4, right? Where am I getting that from? I'm taking what I found there in yellow and squaring both, sum, and then take the square root. So that's 25 plus 4, which is 29. There's no perfect squares in 29, so the magnitude is the square root of 29. Got it? Yeah, those 3 things are pretty easy. Now, granted, we're doing some nifty math there, right? I wouldn't expect that I could hand any of this to my Algebra 1 students for them to make any sense of it. But just like you are now making sense, just a little bit of explanation, they'll make sense of it as well, too. All right, I'm going to say this is the next concept, but it's just really a continuation of what we just did. So what would happen? This is what's called a scalar multiple. We've seen this before, a scalar multiple in previous classes. This is increasing the size of a vector by some quantity, we'll call it k. In other words, if you're given that you have vector PQ and you want to increase vector BQ by some factor of k, you just take everything and multiply it by k. Yeah, that's all it's saying right there. Okay. So, well, that's pretty simple, but what would happen if k was less than 0? In other words, if we multiply it by a -2, what do you think visually would happen? Well, what would happen is the vector would switch directions. Instead of pointing to the upper right, it might point to the lower left. Well, what would happen there? Well, it's still the same math concept. You're still going to multiply everything through by that negative value. And that will flip the vector and also increase its magnitude. Now remember, magnitude, if we actually do the distance formula, we're not going to get a negative value. But notice, what does the vector equal? We can certainly have negative numbers inside that. Well, I'm not going to call it an ordered pair, but that's certainly what it looks like. So what does, when you multiply when k is smaller than 0, it's going to scale it up by whatever that factor of k is, and then it also is going to flip the vector around. In other words, the ray that you drew would be flipped around 180 degrees. Let's do a visual representation of that. Okay, so take a look at this picture right here. So we have what? 1, 2, 3, 4. Well, we don't know if they're rays or vectors. I'm going to say these are all vectors. Not because the picture denotes that. I'm telling you, they are vectors. Okay, so here are 4 vectors right here. So the next concept we're going to talk about is what are called parallel vectors. Parallel vectors. So I think it's kind of clear to see that BC and FG look to be parallel. Well, how do we know they're parallel? By definition, vectors, right, whose direction is the same or opposite, we were going to define as parallel. So notice nowhere in that definition does it say magnitude. Because remember, if this was a ray, the ray would continue forever. So if you can see if these were rays, you could see OA and BC. Well, let's see, OA would go through BC. So we probably wouldn't define those as parallel. We would define those as intersecting rays. But when we talk about vectors, right, that arrow is just showing you the direction of the force. Right? It's not showing that, it's not meaning that it goes on forever. It just shows you the direction and the magnitude of the force. Okay, so we're going to define parallel vectors as vectors. Does that make sense? Okay, so well, clearly it looks like these two vectors are parallel, B, C, and F, G. So the one neat thing there is it says that vectors whose direction is the same or opposite. So the question here is DE parallel to BC? Well, it certainly looks like it. So our confirmation, and oh, by the way, it turns out that all of those vectors are parallel. So it turns out we need a method of figuring out if things are parallel. We know that 2 lines, 2 segments are parallel if their slopes are equal, and luckily for us, nothing changes with vectors. So if 2 vectors are parallel, it turns out their slopes will either be equal. Now be careful with this one. It doesn't say opposite reciprocal, remember perpendicular. It says opposite. And that's going to take the case of BC and DE. Notice those are, I said these were all vectors at the start. Notice that BC and DE are pointed in the opposite directions, right? So we're not going to say opposite reciprocals, we're just going to say opposite. So if the slope of BC is 3 and the slope of DE is negative 1/3, right, then we're going to say that they're parallel. Okay, does that kind of make sense? All right, so that takes care of parallel vectors. Guess what the next one will be? Yeah, that's right, perpendicular vectors. And it's going to be the same drill. So perpendicular vectors are vectors whose direction, notice it doesn't say magnitude, direction is 90 degrees different from each other. In other words, they're perpendicular. And we're going to find this out exactly the same way with slopes. So if the slopes are opposite reciprocals of each other, then the vectors are perpendicular. Okay, or at right angles to each other. All right. Well, we just did 2 things. Parallel, perpendicular, right? That deals with direction. But remember, vectors have 2 parts, direction and magnitude. So what's the deal with magnitude? Do we get something from that? We do. We get something called equal vectors. Now, equal vectors includes magnitude and direction. So check it out. If 2 vectors are equal, well, the direction has to be the same. That means that their slopes are going to be the same, and their magnitudes will be the same. That means when you do the distance formula, you get the same number. So to do this one, you're going to have to use both the distance and the slopes to determine if 2 vectors are equal. And I guess one question would be, well, can we go, if they're already graphed, can we go from the picture? I mean, the answer is yes, but if you're eyeballing something, certainly no, you're going to need to do the math. But if it's very clear, especially ones that start at the origin, right, you can tell just from if it is graphed. Now, if it's not graphed, you're going to have to do the math. Guess what, for homework? Yeah, they're not going to be graphed for homework. So let's do those 3. So let's see how this works. So the question will either read, are they parallel, perpendicular, or are they equal vectors? So this one says, are they parallel? To show that 2 vectors are parallel, you need to show that their slopes are either equal or opposite. Equal or opposite. Equal or opposite. So let's see. Now you're going to think we're going to have to do a lot of work here. We're going to do very little work here to show that they're parallel or not parallel. Because look what it says there. It says that, well, I've got vector PQ is equal to 6, 9. What does that mean? That means the change in x is 9 and the change in y is negative 6. Well, that's what I need for slope. I need the change in y over the change in x. So I just kind of need this in opposite order. So remember, slope is rise over run. Well, the vector definition right there tells us that the change in y is negative 6. And it tells us the change in x is 9. That's the run. Reduced negative 2/3. So what would any other vector that's parallel to this one have a slope of? Well, remember negative 2/3 can be written as negative 2 over 3 or 2 over negative 3. So any other vector that has the same slope would be negative 2/3. And what's the opposite of negative 2/3? Just positive 2/3. So if vector RS has a slope of 2/3, positive 2/3, or negative 2/3 in any one of its forms, then it's parallel. Okay? All right. So let's see. What is RS vector equal to? It's negative 6 over 4. So what's its slope? Its slope is the change in y. That's 4 over the change in x, which is negative 6, right? Rise over run. So that also reduces to negative 2/3. So we got equal slopes. But do remember, if we had gotten a slope of 2/3, positive 2/3, we could have concluded that the vectors are parallel. If these were raised, then no, they would not have been if it was negative 2/3 and 2/3. Okay. What would it look like if they were perpendicular? What would it look like if they were perpendicular? All right, perpendicular. Let's see, they have to have what? Opposite reciprocals. So once again, we're going to get this from slope, and the nice thing about here is half of our work has already been done for us. The slope of vector PQ is negative 6 over 9. All I'm doing is taking those two values inside, because they give me, remember it goes change in x, comma, change in y, and just flipping them around. So negative 6 over 9, which we already said was negative 2/3. Now RS now is at 2 comma 3, so let's see. 2 comma 3, that would be what, 3 over 2? 3 over 2 would be the slope. And notice that 3 over 2 is the opposite reciprocal of negative 2/3. Okay, so we're good to go. All right, remember, if they are equal vectors, right, they also have to have the same magnitude. All right. Seems like we've done a lot. We have to do one more thing. All right. The last thing we're going to do is what's called. So think about this. Let's say let me show you a picture. So let's say you had two vectors, and the two vectors here are in black. So we got PQ and QR. So let's see. Imagine a ball that starts at position P, and you roll it in the direction of Q. And when it gets to position Q, you force it again, but this time in position R. The ball goes from P to Q to R, yes? 2 steps. The result of those two separate pushes, both in magnitude and direction, would be as if you had pushed the ball originally from point P in the direction of R. We're going to accomplish this by doing what's called vector addition. To find out if you had two forces placed upon a ball in different directions, where would the ball wind up, right? This is called the resultant, is called vector addition. And vector addition answers that question of, well, what would be the result of those two forces? Okay? So it sounds really complicated. Oh boy, is it easy. Okay. So that's the general idea. So the general idea is if you want to find what would happen if you put two forces on a ball in different directions in magnitude, well, you're going to do something called vector addition. And it simply says this. Take the first vector, PQ, add it to the second vector, QR, and you'll find out what the resultant vector is. You're going to do a lot of this in physics. Now, I said it's really easy. Well, we know that PQ is, well, change in x, comma, change in y. That would be 4, 1. We know that QR is change in x, comma, change in y. That would be 2, 3. Anybody want to take a guess? Oh, yeah, it is literally that easy. It is literally add the x's, add the y's. Okay, so the resultant vector is 6, 4. Hey, if you doubt me, count the squares. Go from P to R. That would be to the right 6 and up 4. Yeah, it's that simple. So this is kind of weird, right? It comes out of left field, but vector addition is really simple. We better write this down. So vector addition is the resultant vector. That would have been that red line there, when two or more vectors are combined. So a lot of times objects have multiple forces placed upon them. So for instance, think of an airplane. As an airplane flies through the air, it is pushed by the winds. If the winds are coming from the west, the aircraft is pushed to the east because of those winds. But an airplane also has an engine that pushes or pulls it in a direction that's different than the wind direction. Well, where the airplane winds up, hopefully in the right spot, is the result of those two forces. Now, airplanes have a whole lot more forces. It also has lift, drag, and gravity as well too. So it's a resultant of many vectors of force. But there's a quick example of that. All right. And then what's the mechanics behind it? Oh, it's pretty simple. If you have two vectors, PQ and QR, all you simply do is add the x's and add the y's. And that's what that's showing there in yellow. So the vector which is equal to a comma b and the other vector which is equal to c comma d, add those two. So it's a plus c comma b plus d. And I don't need to do an example. It's just literally that simple. Okay. These are questions, I think, 20 through 25. There is some scalar multiplication going on there as well, too, but you guys will be fine with that. It does vector addition and multiplication. Scalar multiplication follows order of operations. So do multiplication first before you do addition subtraction. Okay. All right. Well, believe it or not, ladies and gents, that's the end of the year right there. There's nothing left. You guys have been a great class. Thank you for your patience and your effort of working through proofs. From now on, yes, you will see proofs on nearly everything that you do in math. The proofs will be generally revolves around when they introduce a new formula or something. But from Algebra 2 onward, when you're given something new, then generally we have to prove it to you to make sure that you are on board with understanding of that it is the truth. So, for instance, when you get your next couple things that you get in Algebra 2 and pre-calculus and calculus, those things will be proven to you. Not as rigorous as what we do here in class in geometry. So geometry is your one really strongly rigorous proof class. But nobody does a two-column proof in Algebra 2 onward, meaning like the teacher won't do a two-column proof. They'll just derive a formula, that sort of thing. But they are doing what's called proof. I hope you guys enjoyed, even though it's, a lot of effort, I hope you enjoyed the logic of the class. That's really the beauty of the whole thing is, you're either kind of have a natural inclination to think logically, or some don't. But I would submit to you that even the people who claim that they can't think logically, you guys did a lot of logical thinking, and I certainly enjoyed the time that we had together when we were struggling with some proofs as well too. So with that, I'm gonna sign off. Now remember, we still have next week prepping for the semester final. So you'll still hear from me again, but I did want to conclude this with the end of the school year speech of, it was great, I had fun, and I hope you guys did as well too. So see you guys on Monday.